how many peaks here?
Okay, so the three methyl groups attached to carbon are all going to be A. And then, so there'll be 3 peaks.
Good. Now let's think about the splitting. Now the important point here is you're only split by the non-equivalent hydrogens that are adjacent to you. You only split by the non-equivalent hydrogens that are adjacent to you, which basically means that usually they have to be no more than 3 bonds away. Usually we have splitting for hydrogens that are 3 or fewer bonds away. I'm just drawing a molecular fragment here, but for example, this hydrogen, if it was not equivalent to this one, there could be splitting between these because there's a distance of 1, 2, 3 bonds. So usually we only get splitting for distances of 3 bonds or fewer. Usually there's only splitting for distances of 3 bonds or fewer. So that's what adjacent means here, 3 bonds or fewer. A 3-bond distance. Well, are there any non-equivalent hydrogens within 3 bonds of these hydrogens?
Oh, no.
Now remember, these don't count because they're equivalent.
Right.
These hydrogens can't be split by these because they're in the same group. The closest non-equivalence is the Bs. Well, how many bonds away are the Bs?
4.
4. That's too far away. 1, 2, 3, 4. The closest non-equivalents are the Bs, but we said we usually only get the splitting for a 3-bond distance or less. That would generally happen when the 2 hydrogens are on adjacent carbons. But these are not on adjacent carbons. There's a carbon in between them. That's why they're too far away. So this would be what's called a singlet, because there is no splitting. This is actually not adjacent to any non-equivalent hydrogens. So this would these hydrogens, group A, would give us S for a singlet. What would be the integration of that singlet? How many hydrogens would it represent?
9.
Right.
Wait, so what about the hydrogens that are going to be, oh, they're still 4 bonds away. Okay.
Now how about, say, group B here? Now can group B get split by the group C hydrogens?
Yeah.
Because how many bonds away are those?
1 or 3.
Yeah. They're 1 carbon away, or 3 bonds, which is what we said is when you usually have the splitting, a 3-bond distance. 1, 2, 3, well this is the time when you usually have splitting. So what would N be for group B?
4. Wait, yeah, 4.
Take your time. How many non-equivalent hydrogens are adjacent to group B?
3.
Yeah, maybe you're already doing N plus 1. And then N plus 1 would be 4. That would be a quartet. Yeah, that'll give you a quartet. And then how about group C? What would N be for group C?
2.
And then N plus 1 would be, and that would be a triplet. Notice that neither of these are getting split by group A. That's the key. None of them are getting split by group A because group A is too far away. So this word adjacent here is important. The hydrogens should be on adjacent carbons. Or another way of putting it is there should be 3 bonds or fewer between the hydrogens that are splitting each other. 3 bonds or fewer. Oh, by the way, just I should mention when you're looking at your notes, we didn't start talking about splitting until the second half of today's session, right? So when I was doing the examples in the first half, when I was drawing the peaks, I wasn't showing the splitting. So in your notes, in the first half, you won't see the splitting, not because it's not there, but because we hadn't talked about that yet. So the peaks that I drew at the beginning of the session were a little bit unrealistic because I wasn't showing the splitting yet. I was just showing the horizontal distance on the horizontal axis. All right, so here's a problem from the sample exam. Here's what they called compound 2, and here's what they called compound 3. And we have to say, how will we, let's say that we do an experiment and we're not sure whether we produced compound 2 or compound 3. We did an experiment and we don't know whether it produced compound 2 or compound 3. How can we look at the spectroscopy results from the proton NMR and tell which one it is? I'll give you time to write that down. How would we predict that the proton NMR, if it's this compound, would look different from the proton NMR for this compound? What would be the difference between the two proton NMRs for the two compounds? There might be more than one difference, but what's the easiest difference?
Okay, so for number 2, the hydrogen is right next to an electronegative group. And for number 3, well, there's 2 electronegative, a whole lot of electronegative groups next to the hydrogen.
Right.
And for number 3, it's not that many groups. So that's more electron shielding, de-shielding for number 2. And therefore it's going to be to the left.
This hydrogen here?
Yes.
Okay, so you're saying that these hydrogens would be further to the left. Okay, I think that's a fair prediction. That's a little hard to predict. Well, I think that's a fair prediction because this is between the nitrogen and the bromine, whereas this is between an oxygen and another hydrogen. So I think that's a good prediction. I think that's a good prediction. Good. Any other ways that you could distinguish between these if that didn't work for you?
I'm not sure.
Now, let's think about how many peaks would we predict total here?
2. 3.
Where's the third one coming from?
The methyl group.
That's right. It's easy to forget the methyl group. So that would give us 3 different peaks. Now, how can we tell which are the peaks from these hydrogens and which are the peaks from the methyl?
There are going to be a higher peak for the methyl group.
Because
there's 3 hydrogens.
Yeah. What would be the integration for this peak?
Oh, it's going to be a 3 to 1.
3. Good. And the integration for this would be
1.
Yeah. So it's going to be a 3 to 1 to 1. This will be a 1, an area of 1. This will be an area of 1, and this would be an area of 3. And it would be the same deal over here. Area of 1, area of 1, and area of 3. Okay, good. So it's not going to be too hard to figure out to get rid of the methyl. It turns out the methyl, I don't think, is not the interesting thing to focus on here. So let's not focus on the methyl. It won't be too hard to see which peaks represent the hydrogens on the benzene, because those will have the lower areas. Now, what is N for this hydrogen?
0.
So what would N plus 1 be?
1.
So what's the name for that type of splitting?
A singlet.
That's right. And what would N be for this hydrogen?
3. 4. Oh, yeah, N would be 3. And
3 adjacent hydrogens?
Adjacent non-equivalent hydrogens.
You're talking about the methyls over here?
They're not adjacent.
Yeah. In fact, how many bonds away are they? 1, 2, 3, 4. I think they're actually 5 bonds away if you actually count all the bonds. So these are actually pretty far away from this hydrogen. We wouldn't expect a lot of splitting from these. So what would N be here?
0.
And N plus 1 would be
1.
And we call that
A singlet.
But now let's do that for this hydrogen. What would N be for this hydrogen?
1, 2, 3. I believe that's 3 bonds away. So we have 3, and then another hydrogen, 4. I'm missing something.
So is this hydrogen going to be split by these?
Oh, that's more than 3. Okay, never
Yeah,
mind.
in fact, it's 1, 2, 3, 4, actually 5 bonds away if you actually draw in all the bonds.
Mm-hmm.
I think if this is in the same position as this one is over here, it's for the methyl group. So there's actually more bonds than it seems because I didn't draw in the bonds over here. It's only 4 bonds to the methyl carbon, but it's 5 bonds to the methyl hydrogen. And even 4 bonds might be too much. Okay, well what would N be then for this hydrogen?
1.
Because it's only 1, 2, 3 bonds away from this hydrogen. And we know that we definitely get 3 bonds splitting. We definitely get 3 bonds splitting. So N plus 1 would be,
2.
and what do we call that splitting?
A doublet.
A doublet.